if you went on the meetup groups page, right, the description was amid all the hype, what does it take to become a data engineer? Where do you start your journey, right? So this talk will hopefully give you some insight into where cascading fits into this whole picture. To warm you guys up, although some of you have already programmed directly in MAPREDUCE, I'm going to still start by talking about what Hadoop is, just so that we get the context right. Okay? Now, is it hyped up or it is not? That's a question we should ask ourselves before even getting into this whole Hadoop, or what is cascading, what is pig or hive. This is IDC's estimate, what the volume of data would look like by 2020. And this is directly in implication of Moore's law, right? Your connected world, your density on chips is doubling every 18 months. It becomes easier and easier to amass data. The question is, what do you do with this data? How do you store it? How do you analyze it? And because of a lot of factors in the mid-2000s, Hadoop has become a choice for analyzing massive amounts of data, storing it in albeit a slower manner. There are now tools coming out which let you do things in a faster manner, but spurred by the needs in mid-2000s, Hadoop became as the one of the choices of storing data at scale, right? So I want to just give a little bit of context, why is this hyped up or not, or should we be even worrying about it? Now, we are all Java engineers here. To become a data engineer, what path should you take? Should you directly go into MAPREDUCE? Should you pick some other tool? So these are some of the questions we will try to answer in this talk. First, let's look at what Hadoop is and what problems can it solve. This few slides will be really quick before I jump into Cascading's code and give you some real insight into how to write applications. Okay? So we're going to start about our journey with Hadoop and the programming model which it exposes, which is MAPREDUCE. I'm also going to talk about some patterns in MAPREDUCE and tell you how painful they are to solve. And then we will see how cascading can help you, and then wrap it up with some best practices. The intention of the talk is that at the end of it, you have sufficient knowledge to go ahead and explore cascading on your own. Okay? Cascading is open source. It's Apache licensed. So enterprises are free to use it for whatever needs they might have. It's got a strong community. Last time we heard there were around 220,000 new downloads per month. It's got 8,000 production deployments. It's all completely open, right? So there's a lot of warm and fuzzy feeling you get when you use cascading, right? So we'll slowly warm up to that. So what is Hadoop? I mean, conceptually, it appears to the end user as this one computer which is able to process a lot of data, store a lot of data. So as a user, when you're interacting with it, you're going to just see a single file system namespace. And you can then put files in it. You can process them. So to you as a user, it's all abstracted away. But if you peel these layers off, what is going on behind it? So in a typical cluster, you have a bunch of racks with commodity servers placed on those racks. And then those racks appear to you as one giant computer, right? Hadoop in itself is aware of all this topology, but you are not worried about it as an end user, because your job is to program it, not to administer it. Now, how does the storage work in Hadoop? So there is a storage aspect to Hadoop, and then there is a execution aspect. So let's talk about storage for a little bit. So when you tell Hadoop to store your data, it automatically, in the background, divides it all up and stores it into different blocks. The block size is really large. It's not 512 kilobytes, which you are used to in your regular computers. It was a design decision to make the block size really big. So the block size in Hadoop is, by default, 128 megabytes. You can of course, tune it to whatever you want, but that's the default. Why is it so large? Now, that, again, goes back to what people observed in 2005. Well, you have so much data, and the disk speed has not been increasing that fast, right? So although the memory between disk and the processor has been increasing fast, your I/O speeds have increased, but the disk arm still moves very slowly. So it's much better if you can provide a system which is just doing continuous sweep over data. So you don't want to move around the disk arm too much because the seek time is not increasing that fast, or the speed of the seek is not increasing as fast. Why? Because it's a mechanical system, right? So that's why 128 megabytes is a big block size. Anyway, that was a segue into what I was going to just warm you up for Hadoop, right? Now, also know that when you put something in Hadoop, it gets automatically also replicated, so it's also fault aware, right? So over here, I show you that a file with blocks, just divided into block 1, 2, 3, and they have been, replicated a few times, just for fault tolerance. Okay. Now comes the execution part, right? So we talked about storage, but let's talk about execution. Now, Hadoop will also try to co-locate the execution with the data. You're not moving the data to the execution. You have execution and data happening on one same machine, right? So what does that buy us? Well, it buys us that you are not doing the data transfer over the network, okay? So you're just limited to that machine. If something fails, then of course your process will get automatically rescheduled to some other place. Yeah? As an end programmer, this is how you interact with Hadoop. You're a client. You're called the client. You have a Hadoop daemon running on or a client daemon running on your laptop. So I have this laptop here, and I could be talking to a remote cluster. I can write my job here, and I can submit it from here, and it'll get submitted, right? This people who have programmed in MapReduce know this already. Okay, this is what the physical architecture looks like. It's fairly lot of blocks here, but basically, it's there are two aspects to it. There's a execution and storage. The storage is taken care of by the name node, which holds the metadata about all the different files in memory, right? And the execution aspect is coordinated by job tracker. Now, some of you who are keeping in touch with the development going on may be quick to point out, hey, this is MapReduce 1. This is MapReduce 1. This is not MapReduce 2, which is much more complex. There's a layer called yarn, which is yet another resource negotiator, fancy word, right? But in that, the same idea has been extended. For the purpose of this talk and for what we are talking about today, this will serve us as a guide. Now, when you talk about deploying all this in practice, although those job tracker and name nodes were different, you can sometimes co-locate them as well if it's a small cluster. But keep in mind that task tracker and data node, task tracker is the guy which is responsible for executing the code on your behalf, on Hadoop's behalf. And data node is the guy which is responsible for actual storage of the data. They are both co-located, right? So this gives you the locality. This gives you the code and data locality. That's why it's a system where you can divide up your workload for embarrassingly parallel operations. It is not good for things where you have to do random seeks, right? So shuffling around data over the network, first of all, the programming model doesn't permit it. And secondly, it's going to be really bad if you do that because you're defeating the purpose. OK. So that was a quick introduction over the architecture of Hadoop, how it looks like inside, right? So that's what inside it appears to, that's how it is constructed. But as an application programmer, you really don't have to worry about what's going on inside. That's the claim is, right? But you have to think in MapReduce. So whatever you're writing, whatever application you're trying to solve, whatever big data application you're trying to solve, the first thing you need to do is to somehow mold that into MapReduce. Now, the difficulty in programming on Hadoop is not so much about understanding the distributed architecture. You can understand that in like 45 minutes if you really pay attention to it. It's not that complex. The complication is when you have a new program or a new problem to solve, putting that into MapReduce is hard. It's not easy. And it'll become clear why that is so. So let's take a quick look at what the programming model MapReduce is all about. So as an application developer, you are supposed to write two functions, map and reduce. Everything in the world just boils down to map and reduce. And these map and reduce, for those of you who have programmed in functional programming or Lisp, these go back quite a ways, right? Map and reduce have been known to functional world quite a bit, right? And this is what Sanjay Khemawat and his buddies at Google were thinking of when they discovered this platform, right? So as a user, you're concerned with filling in the details into map and reduce functions. What does a map do? A map simply transforms an incoming key value pair into something, some other key value pair. So on this slide, you see that K1V1, which was the incoming key value pair, got transformed as a result of your processing logic into K2V2. Okay? Now you write this function, and it will get executed on different machines. Each of these machines are going to produce a key and a value. Now what the framework does, or what Hadoop does internally on your behalf, you don't have to worry about that. It collects the values belonging to each unique key and groups them, right? So the second step, the system sorts the keys and groups each unique key with all its values. That is done for you, right? So the second, the third bullet point, that's already done by Hadoop. And then ultimately at the end, the reduce just translates the values of each unique key to new keys and values. So reduce is the function which you will write again, and it's up to you what you want to do with that grouping of values. Now it's deliberately made very, very broad like this, and it's surprising how many problems it maps into. From very, very seemingly simple problems to some of the really challenging problems. MapReduce is quite general enough to adapt itself to a broad variety of problems, right? And that's a hallmark. It's general enough. It's so low level, but it is general enough so that a lot of problems can be mapped into it. From genomics to figuring out something for astronomical observations. It's got a pretty wide variety of use cases which it can be applied to. Okay, so let's look at the hello world of MapReduce. This is the favorite example of all big data guys in batch processing. You read a line of text. What are we trying to do here? We are trying to compute the number of occurrences of a word in a large corpus of text. Imagine that you had a huge, huge file, like petabytes of text, and you want to calculate how many times each word appears in it. How are you going to write that in MapReduce is this example. So what you're going to do is you're going to somehow rely on some facilities which give you the line one by one. Okay? Then once you get the line, you're going to write the map function on it. And in the map function, all you need to do is explode that line into its individual words, and then use that word as the emitted key, and the value becomes 1, right? The value becomes 1. Now, the framework guarantees that the emitted keys, they'll be used as a grouping key, right? So over here, what we see is that each word will be used as a grouping key, and the values will be 1, 1, 1, 1, 1, like that, right? So for instance, over here, when, all the machines which emit when will have 1, when, 1, when, 1, when, 1, like this. And then all you do is you just add up those ones together, so you get a grouping for when, and then you can count it, right? So this will give you the number of times each word appears in this corpus of text, right? So this is the hello world for MapReduce. This way you can analyze data, right? People love this because it gives you an easy way to get started into MapReduce. You understand what is going on in different machines. You also know a little bit about the architecture inside. There are tricks you can do over here to further improve the efficiency of operations. Most often, the clusters are assumed to be both I/O bound and network bound, 50-50% split. But usually, it's the I/O which matters in the long run. So to reduce the I/O, you can have a combiner which offloads some of that reducer function back to map. So there are tricks here you can do, but the broad idea is that you get a grouping, and the system will make sure that those keys get sent to the same reducer, and then you can apply your processing logic. So this word count example, right, it points out a very important thing, that MapReduce is good for embarrassingly parallel operations. You can't use it for something where you have to go and do random seeks. This is the problem. This is the problem. This is a problem which most people face, that you have this well-known data engineering pipeline which you want to compute one function after another, and then filter, and then group, and then aggregate. But you have to think about all those in MapReduce. You have to think about all those in terms of key value pairs. And we'll see how cascading and some other frameworks avoid that problem. Okay, so what are some of the common patterns which Hadoop can allow you to do? Well, filtering or grepping is one very common one, right? So in the same word count, you can also say, okay, well, if my line contains this, I don't want to use it anymore. Just discard it. In that way, you can filter out a part of data, right? You can parse data. You can convert it to some other form. You can count it. At the reducer's end, you just like aggregate all those values, and suddenly you have a count, right? You can bin it because reducers write their own partitions. So you can bin the data as well. And so on and so forth. Now, the last pattern here is chained jobs, which means that you can take one MapReduce job's output and give it to the second MapReduce job, and so on, and construct this large pipeline. That is pretty brittle, by the way. So if doing it by hand becomes very, very problematic in production. Those were the common patterns. That's what you start by doing hello world MapReduce word count. You get into grepping, filtering, et cetera. If you read the book Hadoop, the definitive guide by Tom White, those are the patterns really described well in that group. But then comes the advanced patterns, which is most of the enterprise applications, and that's where the muscle of Hadoop really shines. Like you have things like group by. You want to do group by on large data streams. Do some secondary sort, and these are some of the advanced patterns, which not a very straightforward MapReduce programmer can really program. You have to really think about how to decompose your logic into that. And then you get into problems of scalability. So like Hadoop is linearly scalable. What does that mean? You add more machines to it. Theoretically, your program should scale, right? But oftentimes in practice, it's hard to write these programs because scalability is both a function of your underlying distributed frameworks abilities and also how you write your application code. So it's not that straightforward. And then you get into some very advanced patterns. Now, these patterns, some of them have been solved by Apache Mahout, which is a machine learning library with Hadoop, right? So it has classification, clustering, regression. At my Google Summer of Code, I wrote a machine learning algorithm in hidden Markov models on Hadoop. And that is very, very, like it's repetitive. It repeats itself a bunch of times until it converges to a certain value, right? So these are kind of advanced algorithms. The last 3 slides will just sort of warm up on what type of problems can you solve using MapReduce, okay? So it immediately points back. I'm going to keep repeating this. It's not that easy to think in terms of MapReduce. It's definitely, it may be easy for some people, but to a majority of us, it's not accessible. You start by writing it, you get comfortable with it, but you cannot make that big leap. You cannot be so productive with it, okay? What are some of the troubles? Well, I hate to say that, but not every application you're going to write is a word count. Ultimately, you're going to write jobs which will be composed of one job after another job after another job. And what happens between these 2 jobs or 3 jobs or 10 jobs in the middle? You'll have output of the first job being sent to the second job, being sent to the third job, right there. Now, this is a brittle process, okay? This is very, very error prone. Furthermore, the dependencies between these jobs, you have to manage yourselves, right? You have to make sure that, okay, my first job finishes, I don't have the second one. Okay, well, the second one failed. No, don't stop the third, the fourth, downstream. All this dependency management becomes hell. So it's good to get started in it, but after a while you see that your degrees of freedom, right? What do I mean by that? It means that you can solve simple things simply, but as soon as you start getting more complex ones, it becomes difficult. Okay. Here's an example of a real-world application. Shows you how many, this is one app, but it has 75 jobs in it, which are all chained together in some dependency manner. And all this dependency graph has been managed by some other tool. The point of this slide is to just show you how it's not trivial. It's not trivial to write a big enterprise workflow just using MapReduce alone. But now, given all this, what can we do to achieve to attack problems for our businesses or for any particular use case? Well, one way would be to model the world not as key value pairs, but actually operations on rows. Think of the data as being presented to you as rows, as tuples. As data engineers, what comes to your mind? When you think of data engineers or when you think of data analysts, you think in terms of, oh, SQL guys, right? SQL guys are experts at this. They can take some database, they can manipulate it, they can shape it, they can form different views of it, right? So it's easier to reason about MapReduce, or it's easier to reason about your problem if you view the world as columns of data. So if you have MapReduce, and if you somehow can layer a tuple type world on it, a tuple is just a bunch of objects, and then if you can do some operations on those tuples, then your life becomes instantly easier, right? Because now you're thinking in terms of actual operations on the data which you need to do, rather than doing that big jump. Okay, I need to do this sort, then I need to do this group, but I don't know how to write that in MapReduce. You don't have to do that leap, right? So not thinking in MapReduce is going to cut short your development time quite a bit. You'll still be able to work with large amounts of data, which is often called big data, but you'll be able to do things in a faster manner. Further, not only faster, you can also try to do more complex things in an accessible manner. Okay? Hence, cascading. Okay? So cascading is an open source project. It was discovered, or it was written by Chris Wenzel in 2008, right? Who saw these problems, who found these problems in MapReduce. He was an architect with Thomson's, and he'd been through this. He was involved with the project Nutch from right in the beginning, and he saw these problems. So by 2008, he had a clear idea of what to do, and he started authoring Cascading. It's an alternative API to MapReduce. It's still a Java API. Okay? You're not thinking in terms of key value pairs, how they are being sent around the network, what combiner you need to use, and how to mold your thinking. Okay? You get a bunch of functions, filters, aggregators already in it. You get these constructs such as, it has counting construct, it has like summing constructs, it has grouping constructs in it. It is very easy to write your own, though. It seems very relational on the surface, so things like joins, we have support for that. And the best part is this. As Sasha was mentioning in my introduction, right? Twitter has developed Scalding, which is a Scala layer over cascading. The reason why they could do that was because cascading is JVM, right? It's Java. So any JVM language can call into cascading. So people have been writing their own DSLs on top of cascading, and Twitter's is Scalding. There's also Cascalog, which is closure data log type language on top of cascading. Okay, so this is what cascading is, and now we're going to talk about how to write programs in cascading. Okay, so how do developers use it? Okay, so either you use the inbuilt functions and operations which are provided by cascading, such as first end buffer or count buffer, count operation, and so on and so forth, or you can roll your own. You are also allowed to chain the operations together. So you create these workflows. You have a business problem, but you divide that problem into discrete blocks. Say that my first block will do this, followed by this. And cascading internally will figure out the dependencies between those things. So your cascading program will ultimately get translated into MapReduce code somewhere. But all the dependencies between those jobs, you are not worried about maintaining them. Cascading's planner internally will take care of it. If a part of your logic fails to execute for whatever reason, all the downstream flows will not get executed. So all this dependency management is also built into Cascading. Okay. All right, so let's look at some code. Again, let's start with MapReduce first. Our job here is to not write a word count, but actually do something more useful. So we're going to parse a log file. We assume that we have some log file from Apache server logs, and we're going to just explode it into its constituents. So like for each line, we're going to just apply a regular expression, and we're going to explode it out. and then we're going to save them in a tab delimited manner at the endpoint. Okay? Please bear with me because this seems easy, but I'm going to compare this with cascading, how they both look like, and then I'm going to follow up with an actual cascading code. Right? Okay? So again, this is just a map task. You don't have reduce in this because you're just exploring out the input, right? So what is going on here? This is the business logic over here in the map task, right? So your map function, you're just getting the line one by one, right? Because you have used text input format. You assume that you're using text input format, which is giving you line one by one. You have a regular expression. Actually, let me go to the next slide. So you're going to use in jobconf a particular regular expression, and that regular expression gets applied to a map task. The point is, at each line, you're going to check whether your regex matches that. And then at the end, you're going to just emit that with the output.collect method, right? So for people who have written MapReduce before, this seems fairly simple. But for people who have not, this is the way you write your code with MapReduce, because you have a map function. You're going to fill in those details. The idea here is that the whole API of Hadoop requires you to think in terms of key-value pairs, because it's broad, it's general enough, right? So on this slide, you can see that you've genericized according to the long writable, which is your input key, and the value, which is also your textual input, which is the value. And then you're emitting both text. Text is nothing but a serialized form of string in Hadoop. Anyway, so over here, you're just emitting your parsed out output, okay? And then you also have to specify how to wire everything together, right? So you're specifying that your mapper class was the former slides class. Okay, you're passing in the regular expression, which you're going to use. And then finally, you submit it to the cluster and wait for its completion, right? Okay, so this is how you would do this in MapReduce. Simple enough or not so simple enough, but people have seen this, some of you, and for those who have not, this is how you do it. But now, how do you do it in cascading? So we're still going to do the same thing. But instead of thinking about key-value pairs, we're going to assume that we are getting the line from some source. Okay? Source is a specific type of identifier in cascading. We will apply some regular expression to it, the same regex actually. And we will parse that each line into these 6 individual fields, which are called IP, time, method, event, status, and size. Okay? And further, when we get those, we can still add them together and then push them out to a tab delimited format into a sink. Okay. Before I show you the code, one thing to keep in mind is that cascading operates on this whole metaphor of plumbing. Everything is related to a tap somehow. Taps are the endpoints. You get streams. You get all these metaphors from plumbing. So it's derived from this PMML, which is this kind of modeling, which is very similar to how we would construct a plumbing. Okay. All right. So this is how you would do it in cascading. Okay. So first, before even getting line by line into this, because for those of you who are seeing cascading for the first time, this is too much to take at once. But see right at the beginning, there are no key value pairs in this, right? You're not worried about how one mapper is emitting the values which a second reducer is taking, and so on and so forth. Number one. Number two, you are thinking in terms of what you need to do with data, right? So right from top, what you're doing is you're just opening up a tap, which is a way for you to capture data, okay? So that line, tap log tap equals input path dot matches. It's basically saying that if you specify a URL, you're going to open up a tab called Hadoop file system tab, which is allowing you to read a resource present on Hadoop distributed file system. Okay? That line alone inside cascading will provide you with a stream of tuples. So the I/O details you don't have to worry about, right? And that's similar to what Hadoop also gives you. In Hadoop also, you don't need to worry about I/O as long as you have a particular input format or output format implementation in place. You're not worried about I/O. Similar in cascading also, you're not worried about I/O. You have a tap which is which is responsible for reading the resource and converting the resources objects into objects acceptable by cascading, which are called tuples. Okay? All right. So once you get that, you wire everything up together. Like at the end, like, OK, my tap is going to be processed by this pipe, and I'm going to do those operations. All that is being wired up over here, but your data processing logic is encapsulated within this blue outline box. Okay? So over here, you're saying that I'm expecting my input to be line by line, and I'm applying this regular expression on it. And I'm parsing out for each group, right? Because these are, if you look at the regex, the ones in parentheses, these are groups, right? 1, 2, 3, 4, 5, 6. If you look at right from the left, that's one group, then the second group, then the third, and so on and so forth. And we are saying that the first group, the section of the string matched by the first group is IP. The section of the string matched by the second group is time, and like that. Okay. So because of these lines, what you're getting is columns of data. Okay. Now we get these columns. Although over here we are doing a very simple thing. We are just taking these columns and we are writing them out divided by tabs, right? But you can instantly see you can do much more complex operations on it. Okay. So this is the comparison between what MapReduce will do to this file for writing it out versus cascading, how it go about in cascading. Right. Right. So the question is, he's confused that rather than using string identifiers for the field names, can I give positions? So the answer is yes, you can. I can point you to the right API for doing that, but you can easily get in the field. You can specify this is my 0th column, this is my first column. You can also specify using integers. Okay. Any other questions? OK, so this shows you how to write this program in cascading, take a file, explode it out into individual constituents, and put it in a tab delimited manner on an endpoint. You know, it's all new APIs, so you might be looking at it and being like, what is going on? But it becomes very, very easy once you do a few programs to write in cascading, write your programs according to cascading API. OK, great. So we took a file, exploded it out, pushed it out in delimited manner. Great. Well, that again is like a simple. It's not that complex, right? You could do this in MapReduce too. It was easy. But what changes when we want to filter out some URLs? You know, let's say you want to filter out not just by you want to filter out some log lines just because they contained a particular URL. Okay. And what happens when we want to join these two streams together? Okay. And we want to group those things together on some metric. How about doing all that? Okay. So I'm talking about joining, grouping, filtering things out. And these are data processing tasks, right? These are the tasks which a data engineer would do, right? A data engineer would look at a problem and think about the problem at hand by imagining these things, right? I'm going to group, I'm going to sort, I'm going to process. Okay. What if you want to do all this in one together? Okay. So we are thinking in terms of key. We are not thinking in terms of key value pairs. We are thinking in terms of fields, the columns. So now I'm going to show you an application which does all this. Okay. I have a cascading application which will do these operations on a log file. So what we're going to do, our job in this application, which I'm going to show, is the following. We want to find out what are the users which have accessed a particular URL on our website. Okay. Okay. And we are also going to, but we're not interested in all users which have accessed our website. Okay. We're only interested in some power users, some interesting users. So this could be used for ad retargeting purposes. Okay. So the operations involved in this would be that we're going to get a stream, we're going to divide it into two. In one stream, we're going to filter out only those users which have access to a particular URL. So let's say some particular section of my website. And in the second stream, we're only going to we'll filter out all users but the ones which have a particular score assigned to them, right? Okay. So one stream will have power users, and the other stream will have users which have accessed a particular resource on our website. And then we're going to join them, join these streams together. Okay. Now this is a fairly common, it's not so trivial, right? This is not so complex, but at the same time, it's a good data engineering problem, which we can solve using cascading. At the same time, think about it. How would you do this in MapReduce? Joining itself. What's a join algorithm? Replicated join, where you take one portion of your table and push it around to your cluster using distributed cache. That Hadoop's cache, which takes everything out and puts it on resource. It's complex. That's the point. It's not that straightforward. Okay. So the way I will do this is like I have the application written already in my IntelliJ. I'm going to go over that little by little. It's a lot of code, but my hope is to convey to you how would you do this sort of a thing in cascading, and also illustrate some key elements of the API along the way. Okay? So I already have this application written over here, and while we discuss the internals of this code, let's go ahead and first let it run on my system. Okay? So while it is running, I can explain to you what is going on, and we can see the output later. Okay? So on my machine, I already have Hadoop running here, right? So if I do JPS, I can see the Hadoop daemons. It's running in my local mode. Okay? This is Hadoop 2, by the way, so that's why you don't have job tracker. Okay? Okay, so let's see what is there in my directory right now. Okay? So by the way, I've written this program using Gradle as a build system. How many of you use Gradle versus Maven? Gradle, right? Okay. It's marginally better than Maven, but anyway. So if I quickly show you what build.gradle looks like. So Gradle is similar to Maven. You can use Maven's dependency mechanism with it. Okay, so this is a build tool just like Maven. So these are the dependencies. So when you develop your cascading application, what are the dependencies it requires? So first of all, you always need to have the cascading core libraries, right? And you need to have them in a compile scope. Okay, so the first line, you're cascading core, right? Then you need a second library, which depends whether you're using cascading in the local mode or in the Hadoop mode. If you're using in Hadoop mode, you have two choices. You can either use Hadoop 1 or Hadoop 2. Over here, because my machine is running Hadoop 2, I'm using the Hadoop 2 MR1 flow connector. Flow connector is the layer of cascading responsible for taking your code and translating it into MapReduce constructs. Okay? All right. And then some logging libraries. And then I create this jar with a particular configurations. Okay, so this is what the typical build of cascading looks like. You always have cascading core and another jar which is responsible for whether you're using a Hadoop 1 or Hadoop 2. Okay? So to build this, I can just do Gradle clean jar. Okay. All right. So now Gradle has built this, and it has placed this in the. So it's in the libs directory and under the build directory. Okay. Now I'm going to run this. Now what am I doing in this application? I have the input stored somewhere in my Hadoop distributed file system, which is a log file. Okay. And I'm going to parse it out, do some processing on it. The same thing which I showed you earlier, which I was explaining earlier, and we're going to write it out at some place. What does my input look like? So the input looks like the following. So first, I'm going to show you I'm going to just tail the file which is present on my local file system, but take my word that I've pushed it out to HDFS as well. So tail logs. So it's a NASA log file. Okay, let me do this again. So this is what it looks like. It's just the last few lines because it's a very big file. Anyway, these are the log files from NASA, actual NASA logs. and I'm going to do some data processing on it. I've also taken this file and pushed it to Hadoop distributed file system on my machine, and we can see that in minus LSR. I think it was in right. So I've taken the same file and pushed it out to Hadoop. Okay. All right. So now let me run this program real quick, and then I'm going to show you a visual representation of it, which will become easier for us to reason about, right? So I can do Hadoop jar Okay, so the arguments this program takes are the input path to the Hadoop distributed file system, the same logs file. So this is the input. Okay, and I'm going to store it at a place called output logs. Okay, so while this is running, so I've submitted to the cluster, let me show you how it looks like visually. Now, Cascading is open source, it's free to use, and so on and so forth. Concurrent also has this tool which allows you to debug applications while they're running, and also once they're in production, and that's called Driven. But I bring this up because it's very easy for us to show it here. Full disclosure, I'm not selling Driven here, I'm just showing you how it will look like. Okay, so I have it running here. Okay. All right, so this is what we are doing here. That program, which I'm running on Cascading, this tool at runtime builds up this graph and renders it. Okay, it's good for monitoring and whatnot, but our purpose here is to understand Cascading and what we did in that application. Okay, so let's see. So from left to right, here's what we are doing. We are reading this file from Hadoop distributed file system, right? It's called HDFS localhost, right? I'm also using a tap of the type Hadoop, right? Then following that, so now I'm able to get this file. Okay, I'm getting it one by one. What is the next order of business? Anyone? What's the next order of business? I'm getting this line by line. I have to explode it out into individual constituents, right? So I'm going to apply a regular expression function to it to parse out the lines, right? So this is the function. It's called regex parser, and it is present in line number 79. Okay, so let's see what's in the 79. Okay, so this is the parser I'm applying to my input data, right? Now at this point, I have been able to get from the line all those individual constituents, right? So I have like IP, time, field, etc. Okay. Now what do I need to do? I'm also doing a date parsing. This is technically not needed, but I'm just doing it for illustration purposes. Because this date is of the type string, I'm converting it into a date time. But let's ignore that for a second. Now I'm splitting this into two portions, right? So I have this one stream coming in. I can now split it into two portions, okay? Because ultimately I'll be doing one operation in the top stream, some operation in the bottom stream, and then finally at the end I'll be joining it. Right? Okay. So again, over here I do some filtering, okay, followed by some other operations called retain, unique, etc. But this is what has been going on right now. Okay. Now let's look at how internally are we doing this in code. Okay, that graph was just rendered because of this code. I ran it and it rendered this out. But internally, how does the API work with you to solve this problem? Okay. So right from top, let's look at it. Okay. So first of all, your input path, right, and the output path. So args 0 and 1. We ran the program with input as the logs on the HDFS, and the output we're going to give to args1, right? The input tap, again, in Cascading, everything is to do with a plumbing metaphor, right? So tap is a way for a Cascading application to talk to external data. Whether you write or read, it doesn't matter. It always has to be a tap. How you use it Depends on your particular case. If you use it as a source, you would have to wire it to a particular pipe for a source, okay? So here we say HFS, okay? Similarly, we have an output tap, which is also of the type Hadoop file system, okay? Then we do a bunch of regex parsing here, okay? This line is the one which is taking those lines one by one and adding those regular expressions to it, okay? And then we follow up this pipe, right? You see this regex import pipe? It is being chained here to transform pipe. So this is how you do it in cascading. You get the data out of a tap, give it to a pipe, it's an object, do some processing in it, follow it up by another pipe. And the way you chain them together is by taking the instance from the former pipe and passing it to the second pipe. So this way you can chain them together, okay? Pipes are the objects or the containers to do some processing on data, okay? They are just the containers. What actually goes on inside a pipe is given by the operation the pipe is performing. So the operation in this pipe, basically each pipe is of the type parser. Okay? So input data was coming in and this each did some operation on it. And then we did some date parsing, and then again we followed it up with some other pipes. So I don't want to belabor or drill down into you. I don't expect you to go back and be able to read this code and be able to solve it. The point here is that the operations which you do in cascading are not exactly like MapReduce. You think in terms of columns of data. You think in terms of what problem you need to solve. It comes inbuilt with a lot of these functions. For instance, you have this ability to parse out fields which you don't want. You can retain fields. You can do some unique grouping on it. So this code shows some of those features. Okay. Now, right at the end, once you're done with all your data processing, you have to execute it on the cluster, right? So this particular code block does that. Okay. Now, you have these pipes. You put them together to taps. That becomes a flow. A flow can be started on a cluster. You can give it to a cluster and have a flow, okay? And you can also pass in properties, right? Over here I'm passing the property for the name of the flow, okay? And then I can wait around until it finishes. So this is the way you typically go about writing cascading apps. Okay. Before I go too much forward, I know there are a lot of people who are just looking at this code. If there are any questions I can answer, I'd be glad to right now. Good question. He asked, would you compare this to Pig at all? Yes, there are similarities. So for those of you who don't know Pig also gives you a way to work with Hadoop without knowing MapReduce. You can create these workflows in Pig as well, right? So you can get started in Pig as well. You don't need to worry about what MapReduce is. But here's the thing. Here's the difference. Pig and also Hive, its cousin, Hive. They are both very good for ad hoc query analysis. They are very, very good. You start off by this data set, quickly go in and do some quick and dirty analysis. It's great. Absolutely, you can get started very fast. The problem happens when you're working with the data, and now you have to solve more complex problems. So let's say in Pig, you start off by using its own internal features. You're able to solve a few problems. And then as your complexity increases, you end up writing more user-defined functions in Pig. Basically, you are augmenting Pig with your own functionality, and that is Java. So again, you circle back to Java. Then Pig doesn't have any looping constructs. So now you're like, OK, well, I started off with Pig because it was easy to use. Now my problem has escalated to the point where I need to write Java. Now I end up writing more Java than Pig itself. So that's where the problem happens, that it is easy to get started. To productize your data apps, it becomes very hard with Pig.
Is that likewise with Hive as well, or
similar? Similar, yes. I would say that Pig still allows you to create workflows, whereas Hive is very SQL-like, right? You're just one-off writing SQL statements, whereas Pig still allows you to chain together things. So I would say Pig is slightly more powerful than Hive, but when you compare them with cascading, the comparisons are similar. Good question. He's asking, do you specify the graph of pipes somewhere? It is inferred by the query planner. So you manually, as a programmer, do not have to specify that this dependency comes before this. It is inferred by the flow planner. The question is, this looks very object-oriented. Is it possible to write Lambda? I'd say that, first of all, we haven't ported this over to Java 8 yet. We are still compliant with Java 7, actually 6. And it is more, I would argue that it is more functional in nature, because you're thinking in terms of operations on data, right? To do more functional style programming than what cascading gives you, because cascading is still bound by the constraints of Java, I would encourage you to use scalding, which is a layer of Scala over cascading, which Twitter uses. Yes, the question is, I haven't, he says that I haven't addressed the brittleness problem. Yes, I haven't. I'll be covering that in the next few slides. The short answer is, this logic, if this were more complex, even right now, this will get broken down to more than one MapReduce job. Now, between these jobs, cascading will write out these intermediate files to Hadoop distributed file system. If the first job fails for whatever reason, the second job will not start. Now, when you rerun the same program again, cascading is intelligent enough to start it from the place where it failed, if you have provided a checkpoint. So the question is, it looks like you're doing SQL programmatically, whereas tools like Impala allow you to do SQL directly. So it's a similar comparison to how I contrasted Pig and Hive with cascading. Pig and Hive are also scripting languages. Well, Hive is more SQL-like. Pig is not SQL-like, but the idea is that they can still abstract away MapReduce from the end user and present a convenient interface too. In our experience, when you write data apps, if you don't give developers a way to program that using Java, it spirals out of control. The manageability which you get because of using a Java API is far, far greater than using a scripting tool. You can write these robust programs using API. Furthermore, we are going to talk about in the next few slides about the testing features of cascading. Because it's Java, it can utilize all those test-driven development features, right? So it comes with this array of tools which can let you do things like, hey, check for whether my tuples match this criteria or not. If they don't, then cause an assertion. Then you can also specify if the assertion trips, what to do. Should the application fail, or should it store the tuple for later use? That is number one. So it comes with a lot of test-driven development type features, which are very, very useful. Secondly, one very important difference is also this: operationalizing your data apps. What I mean by that is you can write your application using PigHive or cascading, whatever. But when you take it to production, fact of the matter is you're dealing with semi-structured, unstructured text. You're dealing with low fidelity sources. You're going to get information which is not going to be of top quality. You're going to break at some point, right? Now, when things break in cascading because of some runtime error, it breaks in a predictable manner. If it sees the same input again, it will break in the same way. It will get the same stack trace versus some other query planners which are non-deterministic. So it's very easy to diagnose. Not easy, but it's easier to diagnose the root cause of the problem when you use frameworks like cascading, because they are inherently Java. Third reason is you can get started with PigHive and Impala doing simple things simply. They're good at like starting off very easy. You get really quick boost in productivity. After a while, it becomes more and more messy to compose your logic in them. In our experience, we have found that people who come and learn cascading, either through Cascading User Guide or participating in forums, can write some pretty rock-solid programs in a matter of like days to weeks, versus starting out with SQL-like languages. Right, correct. So his question is it a more problem of hardware, or are we not making VMs fast enough, right?
Yeah, or optimized for SSDs.
Optimized for SSDs.
Yeah.
SSDs are still expensive, right?
Not really, $100 for an Intel box.
And the whole premise is that rather than if you have data all loaded in memory, yeah, it's fast. The problem is, how do you get into memory? So that is a problem which these frameworks like Hadoop solves. You don't have to take all the data and put that into memory. You can work on small sections of it one at a time. That's why it only works for certain class of operations which are embarrassingly parallel. You can't do it for everything. Okay. Yeah. Okay, anyone else? All right. So this is a quick introduction to cascading. This application shows you how to take streams, split them up, merge them, group them, etc. Okay. So now I'm going to go back to my little presentation. All right. So I've been talking a lot about cascading's overall, logic or overall philosophy, why it does things in a certain way. Let me just spend a few more slides to talk about what internally the API looks like. So on this slide, I have briefly described the major points of Cascading's API. Right? Everything revolves around this notion of a tap. Tap is the connector. I'm going to go top down. Tap is the way you connect to data sources or data sinks. Okay? There are different types of taps available to use. HDFS is one of them, JDBC, et cetera. Pipes are the guys which allow you to process data in them. Right? Pipes take implementations of operations. Operations are the ones which are actually processing the data. In this slide, if you see, I put question marks. That means that it's very easy to extend these to your needs. It's not difficult. One of the hallmarks of cascading I found personally is that the code is very, very easy to read and use. If you have a problem understanding some feature of cascading with the API documentation not correct, you can actually read the code. It becomes pretty easy to understand. Go look at the unit tests. They are even easier to understand. Okay? All right. So pipes, they will process data on their own. Right? Now, pipes don't need to be bound to any data source or sink. That means you can take these pipes and have one developer work on them and create the processing logic. They don't need to be executed. You can create these reusable components which you can pass around within your team to do these data operations. Okay? Now, what does a pipe by itself, pipe or pipe assemblies by themselves cannot be executed on the cluster. The term given to an executable piece of pipe assembly is called a flow. How do you get a flow? When you take these pipe assemblies and you add sources and sinks, which are these taps to them. Once you do that, you can actually start them on a particular platform. So assemblies are planned into flows. So over here, you had the same function, which was doing some co-grouping, then aggregating, then group by. And then when you give it to a particular source and sink, this becomes a flow. Now, flow can be executed. Okay. Now, you have created this flow, but there is a layer in cascading internally which will then map all this into MapReduce. Okay. So for simple things like parsing out, if you're just doing parsing or exploding a line into its individual constituents, it just becomes a map task. So then cascading is intelligent enough to set the number of reduced tasks to 0. But in practice, you're going to do a join followed by a merge and so on and so forth. So all that gets internally divided into MapReduce jobs one after another. Now, very importantly, and this was a question, these dependencies between these jobs, they are inherent. They are managed by cascading internally. So you're not managing them. Oftentimes, what happens is you use Pig and Hive, right? You create one flow followed by another flow. You have to manage this dependency somehow. One tool to do this is Oozie. With Oozie, you can create these workflows. One pig script this, one pig script that. Now you have 1,000 scripts lying around. You're managing them. Then they break, and it's a mess to operationalize. Whereas cascading, every dependency is taken care of internally. Okay? And once you have everything, you give it to a client, your Hadoop. Like I showed in my demo, all I did was I created that application, and I submitted to Hadoop cluster. Although the cluster was running on my machine, it doesn't matter where it is running, right? So you can start it from anywhere. So this is what happens. You have a client. It has an assembly, and you submit it to the cluster, but these flows get mapped to different MapReduce jobs. Okay. Now comes the next few slides about best practices. Now there's a trade-off, how big the flows can become. Right? You have a very big flow, it is probably faster. But here's what you can do. A very big flow is not good with just any kind of engineering practice. You need to have well-defined responsibilities for your flow, keep them small to medium, well-defined, your regular, idioms of good software engineering practice. Follow those, okay? Now, what happens if you have one flow, then two flow, the second flow, third flow, fourth flow? What happens then? So far I've been talking only in terms of flows, but here's what happens. When you have a bunch of flows, you can still stitch them together, and that becomes a cascade. So that's where cascading word comes from. You have a pipe, merge to your pipe assembly, which is doing some operation on stream data. Then you create a flow out of it. Then you take another flow, group them together, or rather have them in serial or parallel, whatever way you want. And then that whole thing becomes a cascade. And that can be executed. Okay? Cascading will still internally figure out the order between all these. You don't have to specify. Your question was whether you have to manage that dependency yourself. You don't. It's inherently determined by the flow planner at runtime. What are the relationships between each? Okay. Also, the last bullet point: solve problem first, optimize second. Right? We know this, right? Premature optimization. Don't do that. You start with cascading. Solve your problem first. If at some point you feel that, hey, this is better solved by raw MapReduce, I really want to work with key value pairs, well, all abstractions are leaky to an extent. This is also somewhat of a leaky abstraction. You are allowed to use MapReduce in your flows. You can still use MapReduce as a flow, and cascading will still figure out the dependencies between it. Okay. Not only that, you can actually use Hive also inside cascading. So if you have Hive script, if your organization has invested significant amount of money in creating this Hives flow, you can use that in cascading as well. Testing, we recommend every operation to be unit tested. Okay? Unlike ad hoc querying languages like Pig, Hive, or Impala, you have to create operations which are bulletproof. You have an ability, because cascading has different flow planners. So what you do is you develop your app, you start testing locally, and then once you're done, you can take it to production. And then the very interesting thing is assertions, right? So assertion mechanism in Java, we know this. The similar assertion mechanism is present in cascading as well. What happens is, at runtime, in these pipes, you can inject these assertion statements like, I'm going to assert that the number of tuples passing through this pipe should be 6 number of tuples, like number of columns in my row. Should be 6. If it gets 7 columns, it will trip an assertion. Now, what you do after that depends on you. You can store that for later use, the offending tuple. You can ask the application to stop. You can create all these assertions at development time and then remove them in one shot right at the planner level. So if they are sprinkled around your code, you don't need to worry about it. You can take them all off at the end using a command line argument if you prefer. So that way, you get into all this really good solid ground. You can write robust applications this way. Okay, so in summary, it's an abstraction on MapReduce and other frameworks. What I mean by this? So right now, you can take the same code, run it locally, change a couple lines code, and recompile it, and it will start running on Hadoop 1 if you use a Hadoop 1 flow planner. Next day, if you want to run on Hadoop 2, you can change the flow planner and use Hadoop 2. You don't have to change your core of your business logic. Okay? We also have Tez connector now in Cascading 3. So you can run it on Tez. Tez is another faster Hadoop, I call it. Okay? In Cascading 3, which is a work in progress right now, but by the end of this year, it'll be released, we have plans to open up the query planner. What that means is that if you have your own distributed framework, which you want Cascading to run on, you can program against that interface. It'll be easier to program to write your own adapters to Cascading. That way, once you develop your programming or your data processing logic in Cascading, with just a few lines of code rewrite, you can run it on different frameworks. Right now, we're porting it over Spark as well. Okay? It's got a strong community. Like I mentioned earlier, there were like 220,000 downloads, 100,000 plus downloads last month. Production deployments, I know Twitter runs a lot of their apps on Scalding. It's been tested at scale. Very strong community. It's Apache licensed. So we don't play favorites. We are open to all distributions. It runs on all distributions. We are compatible with Apache Hadoop, and all the other distributions which are compatible with Apache Hadoop will run Cascading. This website, cascading.org/extensions, has a bunch of information about the different projects which the community has created. So we have seen HDFS endpoints and connectors. You can get connectors for exotic data sources and things like Memcache and Parquet and whatnot. Okay. Right, so like I said, cascading.org, please go visit that, submit a patch. We accept pull requests. We are on GitHub. If you need more information for enterprise tool and support, Concurrent Inc. is the place to go. in the end, I'm always there to answer your questions. Okay? Thank you.